That's right. So I'm going to look at this quickly. It was one of the problems I assigned for homework using Riemann sums to find the area under x squared from 1 to 3. And this one, we didn't quite do one like this in class before. How is this one different from all the ones we did in class? It starts at 1 instead of 0. And that complicates the problem a little bit. So I'm going to quickly show you how to set it up following exactly the way we did in class with the starting at 1, and we'll see how that makes it kind of hard. And then we'll talk about an easy trick, which maybe you've already realized, to do it the other way. So this is pretty much just review. If I know the area under x squared from 1 to 3 using Riemann sums, I'll chop it up into n rectangles. And the width is delta x. What's the width of each rectangle going to be in this case? 2 over n, right. So delta x is 2 over n. And if we make the list of all of our points, x naught isn't 0 anymore, right? X naught is actually 1. So my first point, x1, is not delta x, it's 1 plus delta x. And then x2 will be 1 plus 2 delta x, all the way down to xn is 1 plus n delta x. And since delta x is 2 over n, that's just 1 plus 2, or 3. So that's our final endpoint. So in all the ones in class, this 1 was just a 0. Y0 is basically the same, though. Y0 is x0 squared, which is 1 squared. And then y1 will be 1 plus delta x squared. And then yn will be 1 plus n delta x squared. So that much is the same. At least the y's are just a function of the x's. Yeah.
Wait, why is it square from area of x to the 5th from 1 to 3?
Okay, maybe for the homework I made it x to the 5th. Let's just do squared for this one. Yeah, same idea. I think in the other block I just asked them to do squared. So, but yeah, if it was x to the 5th, the only thing that would change is the exponent here. Okay, so those are our points. So now let's figure out what the areas would be. Area is the width times the sum of all the heights. So delta x, y0 plus y1 plus all the way up to yn, which is 1 squared, 1 plus delta x squared, 1 plus 2 delta x squared, 1 plus n delta x squared. Now, why is this expression more complicated than last class? I can't just pull out a delta x, right? And I don't have just the sum of the squares left over. So if I were to continue with this approach, pretty much the only thing I could do is actually multiply each of these things out. So that would be 1 plus 2 delta x plus delta x squared, and 1 plus 4 delta x plus 4 delta x squared, and all that, right, and collect terms and things. And that's pretty messy. And I'm not even going to continue down this path. There are some simplifications that we could do and realize a lot of these terms don't matter. But we're not even going to pursue that.
So how can you do that if there's an infinite amount?
Well, there's not an infinite amount. There's n.
Yeah, that's like a lot.
Well, yeah. So it's not fun. But I mean, you could write out what this is going to be, because all the delta x squareds are going to be multiplied by the squares. and all the delta x's are just multiplied by 2, 4, 6, 8, and then everything has a 1 in it. So you could group those and figure out what the pattern is and write it fairly succinctly. But still it would be messy, and certainly if this was to the 7th instead of squared, then it would be really awful. So I'm going to take a different approach, and like I said, you may have already figured this out. If I want to know the area from 1 to 3, how can I turn that into 2 problems like I had last class? 0 to 3 and 0 to 1, and then subtract. And that's by far the easier way to do this problem. So instead of doing all this, we can just take the area from 0 to 3 and then subtract the area from 0 to 1. Now our area from 0 to 3, what's delta x going to be with n rectangles?
3 over n.
3 over n. And my area, based on what we did last class, right, all my little y values is just going to be delta x squared, 2 delta x squared, 3 delta x squared. Right, because we did exactly this problem last class, starting at 0. So this is really just review. So now I can factor out a delta x squared, right, from each term. So I'm left with the delta x cubed and then the sum of all the squares. Now let's plug in what delta x cubed is. That's 27 over n cubed. And what's our shortcut formula for the sum of the squares?
N squared plus n over 2.
And to the k plus 1 over k plus 1.
Right, into the k plus 1 over k plus 1 plus lower order terms that we don't care about for this exercise. So this ends up being 81 plus other stuff. But as I take the limit to infinity, what happens to this other stuff? It just cancels out because the n cubed dominates. So the limit as n goes to infinity of this sum is not 81, sorry, 27 over 3 is 9. Sorry, that's why you were all staring. 27 over 3 is 9. From last class, the sum of the squares is approximately n cubed over 3. Because the formula we had last class was the sum of n to the k of, well, actually I wrote it this way. 1 to the k plus 2 to the k all the way up to n to the k is n to the k plus 1 over k plus 1 plus lower order terms. Okay, so the area from 0 to 3 is 9. Now mentally redo this problem in your head for the area from 0 to 1. What changes if I go from 3 as my upper bound to just 1? Delta x is 1 over n, so let's write that. Okay, so delta x is 1 over n for the area between 0 and 1. What about the rest of the problem?
You have 1 over n cubed instead of 27 over n.
So I end up with 1 over n cubed here. So everything else is exactly the same, right? As long as I'm starting at 0, then my first point here is just the first rectangle. So my final answer for the area from 1 to 3 is just the difference between these two. So 9 minus the third is 26 over 3. And again, just to connect this to AB calculus, we just showed that the integral from 1 to 3 of x squared dx is 26 over 3. But again, that's just a connection from last year. We haven't made that connection yet in this class.
So I got that.
Look,
Could you have done that instead of all this work?
no, because I haven't defined this or proven that it has anything to do with that. So no.
Never. I was gonna ask if we could just do that to get the context.
Yeah, no, of course not. Okay. So this is areas by the method of Riemann sums. Now, the fundamental theorem of calculus, once I prove it, will tell us that the area is the same as doing an indefinite integral. But that'll be probably next class when I do that. So what I want to do today for notes, I'm kind of jumping around in the book. Today I'm going to show you how to do integration by the method of substitution. So it was u-substitution, if you learned that, that term last year. So we're going to see what u-substitution is. So I'm not going to talk about the area problem at all. We're still just talking about just integration. So up to now, we've talked about the area problem, and we've talked about integration, and I haven't related the two. After I show you the substitution method today, the next class we'll prove the fundamental theorem of calculus, so you can see the relationship between the two pieces that we've been doing. So I'll do those notes starting on the other side of the board. This is new. This is, I think, 4.5 in your book. Integration by substitution. Or it can also be called change of variables. Or you can call it u-substitution. Okay, so these are all the same idea. And the way I'm going to motivate this is start with a derivative, and then we'll integrate it. And the derivative I want to look at, let me just make sure I have the example I want, is this. Let's look at sine squared of 3x. Why is sine squared 3x? And I want to take the derivative of this, but actually what I want to do is not just the derivative, I want to take the differential. So like we did with implicit or related rates, the differential is 2 sine 3x times cosine 3x times, am I done? Times 3. Bingo. dx. This is the only real difference between a derivative and a differential right now, because this is in explicit form and there's only one variable. So how did I do what? How did I get sine and cosine? Somebody tell me. Because cosine is the derivative of sine. Why do I need the derivative of sine? Because of the chain rule, right? Because I did the power rule on sine squared. Right? Because the derivative of u to the n is nu to the n minus 1 times du. Right, so the derivative of sine squared is 2 sine times cosine. Other questions? Okay, so this is a differential. This is a differential. Why am I making a big deal about differentials? Because now that we're doing integration by substitution, you'll see hopefully why keeping up with the differentials is important. So what's the integral of dy? Well, it's just the integral of 6 cosine 3x sine 3x dx. What's the integral of that? How'd you know that? Right, because we just started there, right? Plus c. So integration, as I've presented it so far, is just the inverse of differentiation. This is a differential, or a differential form. And differential forms are the things you integrate. And it may seem like a minor point right now, but the integral of 3x, for example, doesn't make any sense. Because you need a dx after it. Now, when I introduced this last week, I just said, you know, the dx is, right now, it's just notation. Don't worry about what it means. But today I'm telling you, okay, what it means is actually important. 3x dx is a differential. It came from taking the differential of something. So whenever you take the differential of something, you have a dx hanging out. Now, again, when it's just one variable and it's an easy integration problem, you can kind of ignore the dx. It's like it doesn't really matter. But when we start doing these change of variables, you'll see that the dx has an important meaning. And it helps us actually solve the problem. So this is integrating. It's the integration of a differential. And differentials are things that you integrate. Differentials are things that you integrate. So this was easy to integrate because we knew, right, what the original problem was. But if you're just learning integration and I give you this, it's not at all obvious how you would know that it came from that. I mean, just from looking at it, because you've got a sine, you've got a cosine, there's a 6 out there. Where did that 6 come from? Well, what we're going to learn in integration by substitution is sort of a really straightforward programmatic way that you can actually turn this back into that. You can discover where it comes from. And the key is using the chain rule. Because the chain rule was fundamental in going from here to here. Turns out it's going to be fundamental in going backwards. And in integration, we're going to apply essentially a reverse chain rule. So let's see what that looks like. I'll start by just reviewing the definition of the normal chain rule. And I'll put it in a formal setting. The chain rule says this: if y is f of g of x, okay, so a function inside of another function, then dy, the differential, is, we take the derivative of the outside, f prime of g of x, but what do I need to multiply it by? Yeah, g prime, right, the derivative of g. And then, since I'm taking a differential, I keep up with the dx. Okay, so that's the chain rule. Nothing new. But I've written it in this form because now I'm going to make a substitution. I'm going to introduce a new variable I'm going to call it u. And u has this property. So this is new. U is just g of x. So now I'm going to rewrite the chain rule. Now y, it's not f of g of x, which is kind of complicated looking. It's just f of a new variable, f of u, instead of f of x. So that makes dy, according to this formula up here, f prime of u times something. Yeah, and let's back up here to this step. If u is g of x, then what's du? G prime of x, but I'm taking a differential, so it's g prime of x dx. Well, that is just exactly that piece. So du is the second piece of the chain rule. Now I realize at this level this is just kind of abstract. It's symbols. It may not be clear what the importance of any of this is. But once we get it down precisely, then we can apply it. So here's my new chain rule. This is the substitution chain rule. Now let's take both of these things and turn them into integrals. So an integral reverses these. So let's do the reverse. If I integrate this, this just says that the integral of f prime of g of x times g prime of x dx is f of g of x. That's just my first chain rule, basically read backwards. Plus c, of course. So this is a handy rule, but in practice, you may not use it. I mean, this tells you that you can integrate something if it happens to be the derivative of a function multiplied by the derivative of the inside of that function times dx. So if you happen to have something presented to you in exactly this form, then you can integrate it. That doesn't often happen, and even if it does, it can be hard to tell what's f and what's g and what's the derivative. So this is where the substitution method comes in. So let's imagine you are given a problem like this, but it's hard to integrate, it's hard to tell what's what. Well, I'm going to define u as g of x, just like I did before, just like we did over there, because we're still reversing this. So du is g prime of x dx. And now let's reverse our modified chain rule. It just says that the integral of f prime of u is f of u. If I integrate this, I get that. And if you look at this at face value, this should be completely obvious just by definition of integral. It says if I take the derivative and then integrate it, I get the original function back. This is what the method of substitution lets us do. It lets us take this whole messy chain rule step, and by using the method of differentials, lets us turn it into a problem that's really easy to integrate. So let's do some examples, and basically that's what I have planned for class today. I'll do some examples, I'll give you some examples to do, and homework tonight is, to do about 1.5 million of these, so you're really good at it. So let's try a couple. Where did I put my cheat book? Here it is. Okay, the first example I want to do is actually the problem we already did. But let's just pretend we had not started with the original problem, so we didn't know what the integral was just by looking at it. So let's use the method of substitution on this one just to see how it works. So I can integrate this if it happens to be in the form f prime of g times g prime dx. But instead of looking for that, I want to look for something that I can call u.
3x.
I could start with 3x. If I did that, it would turn this basically into sine u, cosine u, something like that.
Sine 3x.
Let's make it sine of 3x. Right? I mean, sometimes u is just that, but for this problem, that's not going to help. Okay, so let's see how this helps. So I've picked a u. Now let's take the differential, not just a derivative, because we need to keep up with the chain rule. So du is 3 cosine 3x dx. All right. Now, if we made a good substitution, then basically this over here, there's going to be a u part and a du part. And when I make the substitution, it is going to be easy to integrate. Well, clearly this is u. And du is almost that. Right? It needs to be 3 times that. Well, why don't I just split this 6 up? And why don't I put a 3 over here and a 2 there? Right? I can do that. So now this really is 2u du.
I have a question. Could you put the 2 on the outside of the...
Absolutely. Yeah, you can put the 2 on the outside, certainly.
So why did we choose to pick sine 3x? Like, why would we want to pick sine 3x for u?
Well, the short answer is we picked sine 3x because it worked, which is not a very helpful answer. But in practice, you just start, you pick a u that you think will work. And if you do the substitution and it works, then that was the right u. If I just picked 3x, I would end up with, kind of like I said, I would have a sine u and a cosine u. I still don't know how to integrate sine times cosine. Right? I know how to integrate just sine by itself. So if you pick a u substitution and it doesn't end up with something that you can integrate, then that was the wrong u substitution. Other questions up to here? Okay, well this I can integrate because the integral of u is just u squared over 2. So it ends up just being u squared plus c because the 2's cancel out. And then for my final step, I'll plug the x back in. So this is really sine squared 3x plus c, which is where we started this lesson. So yay, it is the right answer. But by picking a u variable, and by picking the right u variable, we're able to account for the chain rule in such a way that this integral is now an easy form that we know how to integrate. Questions? All right, let's try another one. Okay, x squared plus 1 squared times 2x dx. So just by looking at it, it doesn't look like it's going to be easy to integrate, just by integrating it straight. Now, based on last week, you could actually integrate this if you multiplied this out, right? Because if you multiply that out, it turns into a polynomial, and that is easy to integrate. But we can do it now using u-substitution. But you have to pick the right u. Mary? X squared plus 1 seems like a good place to start, right? I mean, it's the inside of a composite function. So x squared plus 1 seems like a reasonable attempt. Let's take the differential. du is 2x dx, which also looks good because that is part of my integrand as well. So with x squared plus 1 and du is 2x dx, then my integrand becomes u squared du.
How did you get the du?
I took the differential of u. And it's always critical to keep up with this dx when you're taking the differential. Especially as the problems get harder, you'll need to keep up with that. Okay, and now this is easy to integrate. It's u cubed over 3 plus c, which is x squared plus 1 cubed over 3 plus c. Piece of cake. Questions? Yeah. Nobody knows who's asking.
I forget. What happens to the DA when you integrate? What
Okay, I want to answer a question. Can you get everyone's attention, please? The question is, what happens to the du when you integrate? And the short answer is it just goes away, but it's not magic. There's a very good reason why it goes away. And the reason is because when we integrate, we're not just integrating expressions, we're actually integrating differentials, right, or differential forms. So something that I got by taking, say, the differential of u cubed. The differential of u cubed is not 3u squared. What is the differential of u cubed? Yeah, or du. It's 3u squared du. So integrating this means taking the differential in reverse. So the integral of 3u squared du is u cubed. So the du goes away, right? It just disappears. But the reason it disappears is because this looks exactly like something you took a differential of. It's an exact differential form. It came directly from applying our differential rules.
Can a DU be over a fraction?
Yeah, sure. I mean, you could have, I mean, that's a perfectly well-defined problem.
No, like u squared du over 2.
U squared du over 2, sure. Yeah, that can happen. You can't have that. You can never take a differential and have a du in the denominator, so that would never happen. But yeah, those others are fine. Other questions about this? Okay, let's try another one. A simple trig one. let's integrate 5 times cosine 5x. What would be the right u for this problem? Just 5x, exactly. I don't want it to be cosine 5x because the derivative of cosine is sine, and I don't have a sine in this problem. So u is just 5x. That makes du 5 dx. Don't forget the dx. So when I do this substitution, the 5 and the dx go together. So this is now the integral of cosine u du. Because your goal, when you do this substitution, all the x's have to go away and turn into u's, and it has to be something that you can easily integrate. The integral of cosine is sine. Sine u plus c. Make my reverse substitution. Sine 5x plus c. Questions? Now, I'm going to give you a couple to practice. Tangent cubed x times secant squared x. Try to figure that one out. What's u going to be, du, and all that. Okay, let me work this one out for you, then we'll do a couple more examples. So for this one, u equals tangent, which means du is secant squared. So my substitution, secant squared x dx is du, so this is just the integral of u cubed du. Once I get to here, I can completely ignore the tangent, the secant, none of that matters anymore. The integral of u cubed is u to the fourth over 4. So this is tangent to the fourth over 4 plus c. And you can check that by taking a derivative, because the derivative of this is going to be 4 tangent cubed over 4, so just tangent cubed, times the derivative of tangent, which is secant squared. So tan cubed secant squared. Mike?
Someone was asking me, is tangent to the 4x, is that the same as tangent x to the 4th?
Okay.
What is that 4?
Tangent to the fourth x is the same as tangent x to the fourth is not the same as tangent x to the fourth. Okay. So it's tangent x times tangent x times tangent x times tangent x.
Good question, Simmer.
Good question, Simmer. Okay, here's another one for you with your massive brains.
That's a funny joke.
And the rest of you, too. Okay, another trig problem. Secant to the fifth of 3x times tangent of 3x. Find the right u, and then du, and then substitute, and it's easy.
Is this the right view?
If you let u be secant 3x, then du is 3 secant 3x tan 3x.
3 secant 3x.
Actually, but is this sort of close?
It's sort of
Do I
close.
need to put a 1/3 here?
Yep.
And can I just leave it there?
No, make it over 15.
I did that wrong.
I'm so lost as to how you got that.
I'll work this one out for you on the board so you can check and see. You don't have to look if you want to keep working on it. But this is the correct u, and then du is this. Notice when I take du, there's a 3 because of the chain rule. So if I start substituting into here, I notice that there's a problem. The du has a 3 in it that my original integrand doesn't have. Well, one easy fix for that is if you're off by some sort of coefficient, just add it to the problem. Right, you can do that. But now it's a different problem. So what do I need to do to cancel that out? Multiply by the reciprocal on the outside. This is completely valid because now this is mathematically equivalent to my original integral. But now all of a sudden I have the 3 that I need to make a clean substitution of the du. I'm not randomly adding a 1/3, I'm randomly multiplying it by 1, because 3 over 3 is 1.
Can you just like multiply?
Exactly. Mary?
Oh, can you just like, would you like multiply by like 1/3 at the end?
Yeah, you can multiply by 1/3 at the end, but I'd be really wary of doing that because that means that you sort of mentally kept up with that coefficient along the way. And sure, I mean, if you did this all last year and you're really comfortable with it, then sure. But it's a little, precarious to do that. Okay, so once I've done this, then the u substitution becomes u to the 4th du. Why is it not u to the 5th?
You have to take out a secant 3x.
I had to take out a secant for the du. So the integral of 1/3 u to the 4th du is just 1/3 times u to the 5 over 5 plus c, which is u to the 5 over 15.
No, you're going to see.
Which is secant to the 5th of 3x over 15 plus c.
How many points we get taken off the quiz we could get to see?
15.
That sounds good, yeah.
Everything.
This one C.
I mean, the thing about plus c, honestly, in these kind of problems, it doesn't really matter much. It doesn't essentially affect your answer. Where it affects your answer is if, say, for example, you're doing one of those kinematics problems where you throw a ball or something, you need to know the initial velocity. That's where the c starts to matter, because if you have initial conditions and you actually have to solve for c, if you've done the problem and not kept up with what that c is, then you're going to be completely wrong. So that's why if you forget it now, then when it matters and you forget it, then you're going to be in trouble.
I'll remember.
Is there any situation where like the C will be changed by like if you ever try to do the integration that the C will actually be affected by?
Not if you're just doing this kind of integral, no.
Yeah, but there's no C for different kinds of integrals.
And if you're given some kind of initial conditions in a word problem or some kind of bounds like that, you may have to change, actually solve for c. Yeah, right. Right.
du becomes du over c, but that's what the du is.
Right. Yeah, exactly. Exactly. What about it? Yeah? So the derivative of e to the x is e to the x, and the integral is e to the x, and
How is the graph like e to the x, like the slope is the same as?
we'll prove all that when we get to chapter 5.
Chapter are we on?
4. Okay, a couple more examples. Okay, so a couple integration tricks. Let's look at the integral of x squared plus 1 squared dx. What should u be? So then du is 2x dx. Now, thinking of what we did with the secant problem and looking at this one, what is my integrand missing? The 2, so how can I fix it? A 2 and a 1/2. Right. It's valid because they cancel each other out.
Does it matter if you have the 2 on the outside and like if you had the 2 on the outside and half in front of that?
No, it doesn't matter where you put the 1/2, but the whole reason I'm doing this is so my integrand will be completely replaced by u and du. So if you stick the 1/2 on the inside, then you're still going to have that 1/2. So I think it's just easier to keep up with if you get in the habit of putting it on the outside. But it's not wrong. Okay, so now let's do the substitution. 2x dx is exactly what u is. So the integral of this is going to be u cubed over 6 plus c. X squared plus 1 cubed over 6 plus c. Questions? Okay, let's do a couple more. Okay, square root of 2x minus 1 dx. So what's u? So du is 2 dx. So I need to do the same trick. So 2x minus 1, if I put a 2 on the inside and 1/2 on the outside, then this is 1/2 the integral u to the 1/2 du. And that's just a power rule integral. So it's 1/2 times 2/3 u to the 3/2 plus c, which is 1/3 u to the 3/2 plus c, which is 2x minus 1 to the 3/2 over 3 plus c. So nothing complicated at all about that one. I just wanted to give you an example with a rational exponent. Now the next one we're going to do, the substitution step, is a little bit more complicated. And it looks very similar to this problem. Any questions about this one? Okay. Okay, now let's try this one. Same thing, but instead of a square root, it's just x, or it's x times the square root. So what's the right u substitution here? So okay, let's try the same u substitution. And this turns out that is going to be the right u substitution, but let's see what happens. I still need a 2 and a 1/2. But if I do all this work, what's going to go wrong? You still have an x. Now you may be tempted to try to do something like that. You can't put a 1 over x on the outside, right? You can only do that with constants. But let's go ahead and do the substitution and see what happens, because it turns out this is going to work. 1/2. The 2 dx is du. So it's still u to the 1/2 times du. But I still have an x. Now, just by looking at that, this is not a problem that you can integrate right now because it's got 2 variables and you can't have x's and u's. It has to be all of one or the other. So the question is, can I somehow get rid of that x? And yes, I can. Oh, u plus 1 over 2 for x. Where do you get that? Exactly, because this substitution, right, can be written in multiple ways. So if I take that same substitution and solve for x, then that's completely valid. X is u plus 1 over 2, and that can be plugged in right there. So now this is u plus 1 over 2 times u to the 1/2 du. And that's an integral that only has u's in it. And once I multiply this out, it's just going to be a power rule that I can integrate pretty easily. So what is this? This is 1/4. I'll bring that 2 to the front. And u to the 3/2 plus u to the 1/2 du. And those are easy rational exponents. It's going to be 2/5 u to the 5/2 plus 2/3 u to the 3/2 plus c. In each case, the coefficient is just the reciprocal of the power because I'm dividing by it and it's a fraction, so. Du, no, du is just the differential, right, okay, yeah.
Oh, wait, no.
And now for my last step, I'll plug what u is back into the problem. And I'll get 2x minus 1 to the 5/2 over 10. 2x minus 1 to the 3/2 over 6 plus c. Final answer. So make sure you're okay with all those steps. Any questions? Okay. One last one for you to try. Tangent to the fourth, secant to the fourth. Try to find the right u. Make sure the substitution works.